my master thesis. The topic is called a two-level path planning and monitoring architecture for real-world autonomous driving systems. So this work is part of the GEM project. I'm sure many of you have already heard something about it. We aim to develop a fully autonomous driving system on top of the GEM vehicle, which is an electrically powered and drive-by-wire vehicle modified by autonomous staff. This vehicle is currently stored at the High Bay, which is a facility in the south side of the campus. And fortunately, one of our papers that discussed the current status of the project has been accepted by the ITSC. We just heard the good news yesterday. Okay, so here are a few motivations of this work. First, as we all know, safety is very important for autonomous driving and all other stuff, but it's very hard to achieve. In the past decades, data-driven methods such as machine learning, deep learning, have shown dominant performance in the autonomous driving in multiple areas of autonomous driving, such as perception and also decision-making. But those data-driven methods are very hard to ensure 100% safety because there are always some corner cases that are very rarely happen. So for those data-driven methods, if the training, if those corner cases are not covered in the data set, then those methods will not may not handle those corner cases properly, and failure to handle those cases could have devastating results. Also, there's a certain level of uncertainty on each of the software modules. For example, there might be an error on the location of the GPS. There might also be an error on the pedestrian prediction module, and those uncertainties could have a cumulative effect. So it would be good to have an additional online monitor that constantly checks the safety of the decision made by the autonomous driving system. And we have a few key requirements for such an online monitor. It should have a low latency, which can check the safety very fast. And also it should be accurate. And it also needs to handle those uncertainties properly. So there's an overview of the whole GEM project. The white parts are the hardware that is provided by the autonomous staff, and the gray parts are the software modules developed by our team, and the two blue parts, the path planner and the online monitor, are the main topics of this thesis. So we have a camera in front of the vehicle that will be used to detect pedestrians. And we have developed a decawave system that can localize the vehicle inside the indoor environment. And with those two inputs, we can have the location of the pedestrian and generate a predictive trajectory of the pedestrian. Also, we have a map of the environment containing the static obstacles that will be passed into the hybrid A-star path planner to generate a feasible path that the car can follow, which is a series of waypoints. And and also we have speed and steering data that is provided by the vehicle, and we have a low-level controller that will control the speed and steering of the vehicle to try to follow the waypoints. And also we have the online reachability analysis monitor that will take a look at the dynamic obstacles, which is the predictive trajectory of the pedestrian, and also look at the current state of the vehicle to predict the trajectory of our vehicle and to see if there's an overlap between the predictive vehicle trajectory and the predictive dynamic obstacle trajectory. If there's an overlap, then the vehicle should the monitor should handle it properly, which means we might need to brake or accelerate.
Ted, did you guys develop the speed and steering controller yourselves?
Yes. So our gym team have developed the two PID controllers for steering and the speed.
Okay.
Yeah. Okay. So here's the hybrid A-star path planner. So hybrid A-star is a I just assume that everybody have heard of A-star, which is a very popular searching algorithm. And hybrid A-star is a modified version of it. It's first implemented on the Stanford University's autonomous driving platform Junior, which have got the second place in 2007 DARPA Urban Challenge. So just like A-star, hybrid A-star also search in the discrete space. But besides the discrete space, it also keeps the coordinates in continuous space to generate a feasible path that is in the continuous space. So we can look at the figure on the right. The top one is the original A-star, which will explore all the neighboring states of the current state. The current state is the green cell. But in the hybrid A-star, it will only explore the states that are actually feasible based on the calculation using a vehicle model and the possible controls. So for example, from the current state, which is start in the green cell, suppose we have 5 possible steering, and we have a vehicle model. So we can calculate 5 possible new states of the vehicle, and we can guarantee that those states can be reached by the actual vehicle if the model is accurate. And that's a advantage compared with the A-star. You can see that, for example, the A-star there are certain angles that is clearly not feasible in the real world, but might be generated by the A-star search. Okay. So our hybrid A-star path planner could generate the shortest path through the static obstacles on a given map. And since the running time might be a bit longer, the path is generated offline. And also the path is guaranteed to be achieved by the actual vehicle if the model is correct. Okay. And then we talk about the online reachability analysis monitor. So probably everyone have seen reachability so many times. So I'm not going to read the definition of the reachability analysis. And so we generate so we have I can talk about some of the key concepts. So the state space X, that's all the possible vehicle states in the environment. And the input space U, that's all the speed and the steering controls. The dynamic function F, that's based on the physical model of the vehicle. That means based on the given a steering and speed control and the current state of the vehicle, what will be the next state of the vehicle? And the closed loop controller function, that's our PID controller, which means given the current state and the desired path, what the speed and steering control will be. And also, and the initial states, theta, that's just the current state of the vehicle. Mode P, we'll talk about it later. And the look ahead time T. Okay, so we'll compare the set of reachable states, we call it the reach2, with the predictive trajectory of the dynamic obstacles. If there's an overlap, that means a collision might happen in the future. Also, to cover the level of uncertainty, we expand each of the state to a region with a predefined radius r, and we can adjust r to set to different level of confidence. So here's the pseudocode of the reachability algorithm. So we have an initial car state theta that will include the current location, the steering angle, the speed, and the heading angle of the vehicle. And to look ahead, that's the time. We set it to 3 seconds. And also we have a set of commands P. That's actually the mode P that we have seen previously, which include cruise, accelerate, brake, and emergency brake. So cruise is means that the vehicle will try to follow a desired speed. Accelerate means the vehicle will put full throttle in to achieve a higher speed. That will be useful when the dynamic obstacle is when in a situation where there is an overlap between the dynamic obstacle trajectory and the vehicle's trajectory. But the collision can be avoided if the vehicle can travel at a higher speed. So we can avoid the collision by accelerate. And then there's a brake and emergency brake. The brake means that means a smoother brake. So sometimes if we just brake for a short period of time and then go ahead, the collision can be avoided. So that's the brake mode. Emergency brake means that in a smooth brake, the collision still cannot be avoided. In that case, we'll brake as hard as possible until the vehicle fully stops, and hopefully the collision can be avoided. Okay, so let's go over the algorithm. So for each of the possible mode or possible command P, we will choose a radius r. That's that covers uncertainty, the level of uncertainty. And then then for the to look ahead, we divided it into several segments. For each of the segments, we will compute the vehicle state theta based on the controller and the model of the vehicle. And we will store the states into the path, which is an array of vehicle states that is predicted by the algorithm. And then after we have the full path from 0 to t look ahead, we will expand it based on the radius r to generate the rich tube. And we will check if there's a overlap between the rich tube and the rich set of the dynamic obstacles O. If there's an overlap, then it's not safe. And if for all possible modes, the collision cannot be avoided, it will return the emergency brake. Okay, so that's an overview of the pseudocode. And there are several previous works on the online monitors. So one interesting example is that a group of researchers at CMU have developed an online verification tool that checks the safety of lane changing maneuvers. They've tested on a real vehicle. The difference is that our reachability monitor uses a nonlinear vehicle model, and their tool uses a linearized approximation of the vehicle dynamics. Another interesting example is from a Chinese tech company called Baidu. they have developed the Apollo autonomous driving platform, and they have developed an online monitor for its autonomous driving system using neural networks. That system is independent from other software modules. Since they are using neural networks, their system would be more computational intensive. Also, their system only alarms the safety driver aboard the car, but our system can override the controller and stop the vehicle directly. So that's some differences. Okay, so before the shutdown of the university due to the pandemic, we have conducted several experiments in the facility. So all the modules except all the modules on the overview picture, except the hybrid A-star path planner, have been deployed and tested on the real vehicle. For those who haven't seen the video, the vehicle could follow the waypoints, which is just a circle in the facility because it's a very small one. And the vehicle can brake when it detects a pedestrian in front of the vehicle. That is possible to collect. Okay. And then we also have conducted several experiments in Gazebo simulator. To achieve that, we have developed a high fidelity model of pedestrian and the dream vehicles. The real-time data have been published on the ROS topics. But unfortunately, we haven't tested all the software modules in the Gazebo simulator. So right now, only the 2 modules in this thesis are being tested. So we have used the ground truth from the Gazebo simulator as the input of those 2 modules. And in the future, we definitely should include all the modules. Also, we have created 2 testing environments in the Gazebo simulator. One is high bay, that's based on the actual testing facility where dream vehicle is stored, and also the ECB, which is based on the first floor of ECB of the ECE building. And those 2 environments have been developed by Hebron. I'm not sure whether he's in the meeting yet, but I definitely need to give credit.
Joined a few minutes after you started, I think. Yeah.
Okay.
Hey, Ron. Yeah.
Okay, so here's what the high bay and ECB environment looks like. The red little card is the dream vehicle. Although it looks not the same, but the physics are very similar to the actual vehicle. Okay, so here are some results generated by the hybrid A-star path planner. You can see the paths are relatively smooth, and the test shows that the vehicle can follow the path without any problem. And also there's some result from the online reachability analysis monitor in the Gazebo simulator. On the top, that's what it looks like in the simulator. You can see the pedestrian trying to cross the road in front of the vehicle. And in the figure, the red lines are the predictive trajectory of the pedestrian. And the blue line is the actual vehicle trajectory. And the green area are the reach tube of the vehicle. If you look closer, you can see there are 3 different colors of the reach tubes. So there's a light green one, a dark green one, and a blue one. Those represent the reach tube of 3 levels of confidence. And in this case, the online monitor detects a collision in the future and let the low-level controller to break.
So the gray are the previous and future reach tubes?
I'm sorry, the gray one is the gray one is the path that we want the vehicle to travel. The yellow one is the yellow line, the yellow dotted line is the desired is the waypoints. So you can imagine the gray one is the road, and the yellow one is the central line of the road. Yeah, and you can see the reach tube is very close to the actual vehicle trajectory. Okay, and then there's some performance analysis of the online reachability monitor. So we measure the running time with different look-ahead time. It proves that the reachability analysis can be finished within 0.1 second, which is a very small number. And also the running time is growing linearly with the look-ahead time. And all these numbers are generated by running the software on a laptop with NVIDIA GPU.
I have a question. How many steps in your look ahead time?
I mean, time steps. Yeah. So the time step. So the look ahead time is shown above, and in our case, I think the time step is like 0.3 seconds or something.
So 10 steps, maybe.
Yeah. So for the first one, it's like 10 steps.
Okay.
Yeah. And also we measure the accuracy of the reset. So we take a look at each of the reset and the comparative with the actual position of the vehicle. We define it as accurate if the reset include the actual position of the vehicle. And you can see the accuracy is about 98% in most of the cases. And also the accuracy will drop as the look ahead time increases or the speed increases. Okay, so there are several conclusions. So this thesis present two-level path planning and monitoring architecture. And the path planning module used a hybrid A-star algorithm, could generate a path offline, which the vehicle can use to navigate through static obstacles. And we developed an online monitoring module based on reachability analysis, which could simulate the vehicle movement and check the safety interaction between the vehicle and the surrounding dynamic environment in roughly 0.1 second. And for future directions, first, we definitely want to do more testing scenarios, both in real world and the Gazebo simulator. In Gazebo simulators, we have developed several testing scenarios, but due to the physics constraint of the real world testing facility, it's very hard to achieve those. So we definitely want to do more complex testing in the real world. And also, currently the vehicle and environment models are relatively simple. We use a bicycle model for the vehicle, which is clearly not exactly accurate. So we want to try something more realistic and see what will happen. Also, there's some room for the software optimization on the hybrid A-star path planner. We hope that it can be finished in near real time, so that we can constantly generate the path for the vehicle, not just the generate. Right now, it's only generate offline, which means we generate the path in the beginning, and then the vehicle will follow the path as long as everything looks fine. If there's something happen, the vehicle has to stop and then spend some time to generate a new path and then follow it. Okay, so that's all for my thesis. Any questions?
I had a quick question about the hybrid A-star performance. So you guys have only tested it in software, right?
Yes.
And you do the path planning before any of the motion starts with the static obstacles in mind, or do you do it? I think you mentioned something towards the in your conclusion, something towards the to the effect that if you encounter a dynamic obstacle, then the vehicle does the hybrid A-star path planning again. Is that right?
Yes. So in the beginning, we have a map of all the static obstacles, and the hybrid star will generate a path based on that. And if the vehicle stops, it can generate a path again, which include new emerged static obstacles. But due to the computation time, it's impossible to cover all the dynamic obstacles in the path planner. That means it will take too much time, and the vehicle basically cannot move properly.
Can you have you looked into treating the dynamic obstacle and the predicted uncertainty of the dynamic obstacle itself as a new static obstacle? Is that something that is infeasible or not a good idea? Or
So the hybrid star path planner could take several seconds to finish. So if we take the dynamic obstacle into consideration, that might be a problem because we need to wait until the new path is generated. Then the vehicle move forward a little bit, and then the dynamic obstacle change its position, and then we need to calculate the path again. That means the vehicle cannot run smoothly. So that's why I say I want to have some optimization on the path planner. So if the path planner can be finished very quickly, then yes, we can include the dynamic obstacles in the consideration.
Maybe we can, maybe you can plan the whole path offline and then handle local replanning online, like just to return back to the same path that you planned for while avoiding the obstacle instead of planning the whole path again.
I think Minghao is doing something similar for RRT.
I see.
Yeah, I'm doing